a little bit about the ampacity of conductors and what's not. Okay, so a few things. I hope this is not new topic for you, because this is probably the third time that we're going to be talking about conductor ampacity, guys. And the reason why we do that one, we did it for residential project, we did it for the commercial project, and now we're doing it for the industrial project. Three times, hopefully the third time Adam will kick in. Probably you heard it even more because you came from the wiring side. Okay, so wiring tables. So talk about wiring tables, guys, and determining the size of the conductor. A few rules you shall not forget. That's why they hire us and pay us. Select conductor for proper wiring from the proper wiring table. What type of insulation we need to connect? What type of size of wire we need? Different type of wire insulation is so the size of the conductor, the wire of the insulation, insulation characteristics. We'll talk about this one, THHN versus THHW and what's not. Correction and adjustment factors. Every time you put the conductors in together or a different temperature, you have to apply a correction factor to determine the most important things, Adam, which is the conductor ampacity. So if anybody ever told you how much current a conductor number 12 THHN can carry, if anybody, Adam, ever told you a number 12 THHN conductor, how much current that conductor carry? You know what your answer should be? I don't know. Why don't you know? Because, well, it depends. Are you going to put it in what type of temperature you're putting it in? And are you grouping it with others, right? So, and what's the voltage that you're going to be pulling that conductor at? So the voltage, the insulation, the size number 12, the insulation of the conductor, the voltage of the conductor, guys, the temperature, the ambient temperature, and the way of wiring it, grouping it together, will decide how much current the conductor number 12 can carry. So I can make number 12, guys, carry 20 amps, or I can make it carry 1 amp. 1 amp. You cannot pull more than 1 amp if you group it together and put it in a very high temperature. So be aware that when you have a conductor, depending upon how you wire that conductor, do you group it together with others? Do you put it in an ambient temperature other than 86 Fahrenheit? It will decide the ampacity of that conductor. I hope you guys know that. It's not new to you. Then we get into the voltage drop problem, guys. So we talk about the resistance of the wire. Now, in an industrial project, Adam, you have long runs. Did you guys see the plug-in? The plug-ins were 106 feet. These are long runs for branch circuit and what's not. So you get into the voltage drop problem. Tomorrow, Derek, we will do calculation about voltage drop 3-phase and single phase. So then we need to determine the proper size for the loads located long distances. I always, when I teach ampacity, I said, guys, you decide the conductor ampacity based on 3 ways. Number 1, if it's continuous load, 1.25. Number 2, if it's times the full load current size. Number 2 is based on derating ambient as well as bundling. So you have to make sure that it's the size is based on derating. And number 3, based on voltage drop. 3 sizes. And then you come up with the right size. 3 methods of calculation, then you come up with the right size. List the requirement of using parallel conductors. You guys have been parallel conductors. We have 11 sets of 500, I think, for the switchgear 4000 amp. What are the requirements for parallel conductors? So we'll talk about the requirement for parallel conductors. Then, I know you're not electricians, guys, you're designers, but when you become a project manager, project leader, you should be able to know a few things about commissioning of a building. Before they energize a 4000 amp switchgear, guys, what they do is mega ohm meter. They test the insulation. So make sure the insulation has not been damaged. So talk about testing the insulation via mega ohm meter, pumping that DC voltage across the conductor. Okay. The article that you probably should forget if you have to stay in this business, Derek, you might forget 35W, but 310 should not be forgotten. You know, 35, MSA 35W, right? Could be forgotten, but not 310 though. 310, that harsh a little bit, wouldn't it? So 310 is very, very important because it talks about the general wiring. How do you wire from a shed into almost a nuclear plant? The wiring methods they use in all these applications that we have in the US and elsewhere. Okay, it lists conductor applications. Allowable ampacity for conductors in this article. and give the insulation information about all the conductors that we use, high voltage and low voltage. Use to determine very, very important thing, the conductor size. Do I need number 12 or do I need number 4/8, right? Like we use in the US. Correction factor must be applied if your ambient temperature other than that 86 degrees Fahrenheit or 30 degrees Celsius, and if you have 4 conductors or more, you shall apply the rating factor. You know, that's the rule. Why? Because higher temperature contribute to deteriorating of the insulation, stressing the insulation, always. Temperature, if anybody ever asks you, how does the temperature affect electricity? Enemy number 1 of electricity, electrical power, is heat. Cold is good. A cold temperature like in Minnesota now, all these transmission lines are just sitting there being cooled and nice, below zero. Hot temperature stresses the system because electricity creates heat, right? As it goes through the wire, creates heat. And now if you add more heat, you need to dissipate that heat. Now if the surrounding ambient temperature is hot, guys, can you dissipate heat in a very hot environment? You can't. So the insulation will deteriorate. Very, very important. Okay, so that's what Article 310 does. Okay, insulation type. When you have, we talk about, guys, the insulation like T, H, H, W, T, H, H, N, and what's not. It will, the insulation type, Adam, will decide the amount of current a conductor can carry. Very, very important. So the current, how much current can carry, and also the voltage rating. The voltage rating, like THHW is rated for 600 volt. MV90 can be rated for 15K, 15,000 volt. You can see the insulation size, MV90 or MV105, I can get it to 5K, 15K. But THHN or THHW, you're looking at 600 volt or less. 600 volt or less. So the insulation will decide the voltage level, 600 volt, or 5 kilovolt, or 15 kilovolt. And of course, the current, ability to carry the current. Is it carrying 50 amps or 100 amps or what? Depending on the insulation that you have. Okay, the amount of voltage and insulation can. So the voltage will be determined also by the type of the insulation and the thickness. The higher the voltage, Derek, the thicker the insulation. If you look at the medium voltage, you guys have seen my cable, the medium voltage cable, you can see very thick insulation to hold the voltage. Voltage tend to like to escape, guys, so to run out of the conductor. So what they do is they have the cover inside of the aluminum around the insulation to hold that voltage in the wire, so it can direct the power to where it needs to go, not everywhere else. You know, when the insulation deteriorates, you know what the first thing that happens? You have a ground fault. What's a ground fault? The voltage jumps into the conduit and goes down to the ground, disappears. So that's what the most important thing about the THH and the THHW. Okay, here's your cover. So the wire will go right through this cover aluminum. That's my, say 100 amp, my 100 amp carrying it. The insulation here is for the voltage, say 600 volt, THHW, and this is, say, 100 amp. Let's just say we're pulling a 1 knot AWG inside it. So what does the insulation do? Hold the voltage inside the conductor, does not allow it to escape. And the thicker the insulation, the higher the voltage level that you can insulate in the conductor. The thicker the conductor, the more current you can do. Also the insulation, guys, it holds the voltage and it also holds the heat, right? Because of the type of the insulation will decide how much current the conductor can carry. Because yes, it holds the voltage, but also traps the heat. That's why, Adam, the best conductor that can carry the best current, you know where? If you put a conductor up in the air outside in the winter, that's the best application for that conductor. No insulation, nothing, sitting up there, bare naked, and the current is going right through it, and the air around it is cooling it. That's the ideal situation for a wire, right? Now, can we do this one in a room like this, gentlemen, without killing people? Can you put a hot bare wire running all over to feed all these loads? You can if you don't care about safety. So we have to insulate them, unfortunately, because we have to put them in buildings. Okay, conductor metals. The metals that we use, the most common, guys, is typically copper and aluminum. And they also have a combo of copper-clad aluminum, a mixture of copper-clad aluminum. These two are, the code treat them the same, and the cover is treated differently. So you're going to find most of the stuff, the engineered project asking for copper. A lot of feeders could be aluminum because it's cheaper, easier to install. So your option, engineered projects typically go for copper. Then we get into the correction factor. Correction factor, guys, ambient temperature. Like I said, enemy number one atom of electricity is what? Heat. So that's why the ambient temperature is very, very important, the surrounding temperature, in determining how much current a conductor can carry. We have multiple charts that guys provide, multiple charts, you can look at them, that provide calculation between 70 Fahrenheit all the way to 170 Fahrenheit temperature, the rating table. After you reduce the current of the conductor based on its insulation, then this becomes the conductor ampacity. And you guys have done that before. This is nothing new to you. Then you get into something called more than 3 conductors in a raceway. So if the ambient temperature is other than 86, you derate. If you put more than 3 hot conductors in a raceway, you derate because of that combination. Why do we derate inside a conduit or a cable, guys? Because something called combined heat dissipation from all conductors, higher raceway temperature. If you have more conductors in one conduit, all of them are generating heat. They will be exchanging all these heats. The conduit will be hot. The insulation will deteriorate. So the smarter than Chad long time ago decided if you put more than 3 hots carrying current, you got to derate. So what do they do? Then the ampacity of the conductor must be derated, like we have done. We will look at these tables, guys, adjustment factors for 310.15b2. We'll give you the factors. Conductors are of different systems. Install the conductors in the cable tray. If you have 24 inches or less, the conduit is just 24 inches or less. That derating 24 inches or less, then you don't have to derate. But you have to derate if you put them in a cable tray. You have to derate if you put them in a conduit. And the insulation, when you group them together, have to be rated based on the highest voltage inside the conduit. So if you use underground conductor, guys, they have multiple tables that can get you 310.81 all the way to 84. These are conductors for underground ampacity. And if you have higher voltages, they have a multiple 310.60. I think they changed it now. That can get you buried duct banks. They have buried duct banks, center point of individual, and they place them at 7.5 inches apart as they put these duct banks, and they pull all these conductors inside them. So that's my duct bank, and you put all these conductors inside that duct banks. These tables will allow you to find the ampacity of these conductors under these circumstances. If all hell break loose, Adam, you are, under engineering supervision, allowed to use a table to find the ampacity of the conductor and the derating factor, calculate conductor size and resistance. You can use it under engineering supervision. You know, you can have a calculator. We have softwares that calculate the ampacity. You can use the tables or the engineering formulas that you can use for derating or calculating the ampacity of the conductor. This is for derating. Okay, I'm going to show you guys before we go to the long wires. I'm going to show you a couple of tables, and you should be familiar to you. If it's not, we're in trouble. Okay, here's the first table, Adam, that we need to pay attention to. This is table 310.15, 310.104A. I want to bring to your attention, guys, this is only for 600 volt. If you look at the insulation that we use, look at this one. This is R, for example, RHH. Thermoset is the type. It's rated for 90-degree dry and damp location. The sizes can go from 14 to 2000, and it gives you a few information about the jackets, the overall cover, and the thickness of the insulation, the thickness of your insulation. Any comments, guys? Any question how to use this table? And any comments how to use this table? Please, I know we've done it before. So here's on my cable. It gives you the insulation type. The type letter that they use, the trade name, the type letter, the maximum operating temperature, application, where do you use it, dry or wet or damp, insulation, thickness of the insulation, and a cover.
I'm going to flip into the second one. The most common one that you're going to be using, Adam, is heat resistant thermoset. It's called THHN, 90 degree in dry and damp location. 14 all the way to 1000 kcm, and nylon jacket or equivalent wrapped it. Another one is THHW, guys, 75 in wet location, 90 in dry location. And here's all the sizes. Another one that we use is THW-2, that also can be 90 in dry and wet location. UF cable is here, so please make sure you guys familiarize yourself with this table. Look at this one. And then I'm gonna stop. This is XHW, 90 degree dry and damp location. In wet location, it's rated for 75. It tells you a little bit about the sizes that it comes. And the last one is XHHW-2, 90 degree dry and wet location. And it goes from size 14 to size 2000. Any comments, Derek, my friend? Any questions about these tables? Do you guys know how to use this table? Can I have thumbs up, Chad? This is not the first time that you have used them. Okay, that's all I care. Always look at the insulation and the temperature, because the temperature will decide how much current the insulation will carry. If you go to the next one, guys, here's the Ampacity 310.15B16, and you guys have used that one. Look at the insulation here. We said we use these one, the table, very important. The 75 degree column, we use it if the load is more than 100 amp. If you have a load more than 100 amp, very important, 100 amp or more. If conductor is more than number 1, and of course the insulation have to be rated for these, you use 100. You use this one if the current is less than 100 amp, less or equal 100 amp. If conductor is less than number 1, you default to this one, unless you know that the lugs are rated for 75. That's your default. So almost always in an industrial plant, guys, you're almost always defaulted to 75. The 90 degree column is only for derating. Derating. You do not size things based on 90 degree column. You derating. So, Adam, I have a number 8 conductor. Your default, how much current carry the standard condition is 40. If the lugs are rated 75, you can make it carry 50. If you need to derate this baby, and it's THHN, if I use, say, it's a THHN conductor, I can make it carry 55 and start derating at 55. Any comments, guys? Any questions? Any comments? Any questions? This column right here is only for derating. You cannot size based on 90 degree. I will remind you guys, this side is aluminum, this side is copper. You always default in an industrial plant. Adam, you are almost graduating with me. Now, when you default, when we start looking at your sizing and say, how do you going to size, Chad? We're going to default right to the 75 degree column. What are the rules? 100 amp, more than 100 amp. Conductor is number 4, or the lugs are rated for 75. In an industrial plant, guys, almost all the panels and everything and transformers are rated for 75. So your default will be where? 75. Why? Because the number 8 has 4. Look at this. It can carry 40, 50, or 55. Which one am I going to use, Chad? Which one? You're going to go in your default for an industrial is going to be 75. Why? Because typically the lugs are rated for 75. If they're not, then you apply the 100 amp or less, or conductor is number 1 or less. So that's the default for all these guys. Typically the default right here, that's your default. Anything lower than that in this area here, your default becomes 70. Any comments how to use this table, guys? It's a crime, Derek, to leave Dunwoody without knowing how to use this table. Really. So where do we default as an industrial now? 75 degree column. When would I use to the 90 degree column? Only if you're derating, based on temperature or bundling. Okay, so that's that table. And if you guys look at the bottom here, Adam, my friend, now if you go at the bottom, from here all the way down, guys, your default would be to look at this Ampacity. That's my default, right, based on the code. Unless you know otherwise. And here above, the default for these is here. Can you guys see that? Up to number 1, including number 1, default is 60, unless you know the logs. You go ahead and 1 out, your default is 75. No question asked. Unless you know what the logs are rated for. The logs are 75, you always size based on 75.
These amps right here, this is only for show and tell and derating only.
Show and tell and derating. I want to bring
Bring to your attention, guys, the bottom here, where it tells you the rating. You have to derate based on
ampacity correcting factor of temperature. All right. So 17 atom, this one is like 315B17 is only for single insulated conductor up to and including 2000 in a free air. If you put them in a free air, then you have to use this 17. Very similar. Derating
tables. You guys have seen the derating tables before. I hope.
Derating table, if the ambient temperature, guys, if your ambient temperature is other than 86 Fahrenheit, you have to derate.
So here's how this goes. Let me just go directly here.
Derek, my friend, 310.15B,
B8 will tell you if you are other than these two temperature, you must derate. So for example, let's just say we're Fahrenheit.
Oops. I want to go up a little bit with the Fahrenheit. So let's just say
the ambient temperature, guys, is this in Fahrenheit 113. And if I have a 100 amp conductor, that 100 amp conductor can carry, if the insulation is 90, it can carry 87. If the insulation is 75, it can carry 82. If the insulation is 60, that conductor can carry 71 amps. So if you have TW, this is THW, this is THHW. Same conductor can carry different insulation based on
different amps based on the insulation. Any comments, any questions? Adam, comments, questions? If I test you on that one, will you guys get it? Cool? So if you have 100 amp and the insulation is TW, you can only pull 71 amps out of it. If the insulation is THW, you're pulling 82. If the insulation is THHW, you're pulling 87. Can you guys see the impact of insulation on the amps? Huge impact. Based on what insulation you have. Okay, cool. So we got that one under control.
The second thing that we bundling, Adam, and we have done that one. It's going to be on also in one of our tests. Yeah, too. Okay, for bundling, look at this one. If you bundle, if you have up to typically 4 to 6, you will have 80%. So if you have 100 amp conductor, now you can only get 80 amps out of it. If you put 6 hot conductors into a conduit. So you don't want to go lower than that, guys. Sometimes also you can go as low as this. So if you put 9 of them, you can only get 70 amps out of them. If you are full and you want to put 41 of them, look at that. I want to put 41 conductors in the same conduit. Look how much current I can pull out of this 100. I can pull only 35 amps. So Adam, look at this. Based on how many, if you have a conductor that can carry 100 amps, if you put it with 6 conductor, you can get 80 amps out of it. If you put it with 9 conductor, you can get 70 amps out of it. If you put it with 41 conductors, the same conductor can carry no more than 35.
Any comments, guys? Any questions about this bundling? Derek, does it make sense? Matt? Okay, so that's very, very important, guys, to understand that one. And you're not going to hear Chad talk about this more. If you get out of here, I'm not telling you, and you still don't understand it, ask me for a refund. Okay, so that's basically it in terms of the ampacity, guys. That I want to focus on. So let's just, the second part is voltage drop, which we will be doing a lot of calculation tomorrow too for voltage drop. So let me go back to my presentation and we'll talk about the K and the voltage drop in a second here. Okay, so we got that one. Now, we know how to use the tables and the derating. Now, Adam, if the distance is, say, 100 amp branch circuit or feeders or 80, you start doing voltage drop. Guys, the longer the runs, the more voltage drop you lose. The code allows you to lose only 5 volts, otherwise 5% total on feeders and branch circuits. So what the code allows you to do is feeders and branch circuit. Here's my feeder. Here's my branch circuit. My branch circuit here. And the feeder, we do 3% on feeders, 2% on branch circuits, for a total of 5%. If you go higher than 5%, your system could malfunction, could not work efficiently, so it becomes a problem. if you go lower than. So if your voltage is 120 and you drop 5% to the other end, your equipment might not start. If it starts is not efficient, it's going to consume more power than it should. So it becomes an issue. By code, you have to adhere to these rules. So because of this, guys, we have to find the resistance of the wires. The resistance of a wire is a function of the material from which it's made. Copper have less resistance than aluminum. Diameter of the wire, fatter, bigger diameter will give you more current. And the length of the wire, longer wires will give you more resistance, more voltage drop. And of course, the temperature of the conductor have effect on it too. So there's some materials, guys, the resistance will increase with temperature. Other materials, the resistance will decrease with temperature. They call it a positive coefficient. Material which resistance increase with temperature is increase have a positive coefficient of temperature. Believe it or not, these characteristics, guys, have a lot of application. Okay, so the diameter, the bigger the conductor, the less the resistance, the more current you can put through. The longer the conductor, the more the resistance, the less current you can go through it. Okay, because that conductor, guys, ultimately have a resistance inside it, right? It resists the small but a big deal. The way they calculate the resistance, Adam, is by having this formula. This formula is called K times L. K times L divided circular mil will get you the resistance of the conductor. L is the length, you can see very easy in feet. R is the resistance of the conductor, obviously. K is the ohm per mil foot, ohm per mil foot factor. But by doing it this way, guys, you find the resistance of the conductor. If you multiply R times I, that will get you the voltage drop. The formula that we're going to be using for voltage drop, guys, which I'm going to be going over it tomorrow, there is a formula that's called voltage drop equal to K-I-L over circular mil. So this is the formula that we're going to use for voltage drop. If it's three-phase, voltage drop formula will be 1.73 times K-I-L over Cm. These are the formulas, Adam, that you're going to see your friend Chad tomorrow going over in examples. Cool? Can you have thumbs up, Chad? Okay. So be aware of that one. That's the calculation. This is just analyzing, guys, in a three-phase system. In a three-phase system, only one conductor can reach the max. Can you guys see the max of this conductor while the other two conductors are minimum? So one conductor will reach the max at a time. Because of this phenomena, because they're 180 degrees away from each other, so then you can see at one time the maximum will be going one way and the other is going the other way. So because of all this phenomena, look at that one. At certain time, only two conductors will have current. Because of the three-phase characteristics, guys, when you have a three-phase system, instead of adding the resistor for all the feeders, A, B, and C, what they do is they use the 1.73 to find the voltage drop, the 1.73 to find the voltage drop. Can I get you guys in a three-phase system, because the current is not max in each and every phase at the same time, they have an average value of 1.73 when they calculate the voltage drop. That's all what you need to know on these. Okay, so that's what the voltage drop. Again, I promise you, my friends, that we will be doing calculation about voltage drop tomorrow. A lot of calculation about voltage drop. And we'll go to table 8 and what's not. When you parallel conductors, Adam, here is a phase A, phase B, phase C. Here, I'm sorry, this is phase A. Here's three conductors, 1, 2, 3. Here's phase B, and I'm putting them in the opposite direction here. And here's phase C. There are three conductors in each phase. When you parallel conductors, the most important thing, guys, the material must be the same when you parallel them. The area, circular mil, must be the same. The insulation must be the same. And they have to be connected, the terminated in the same manner. The conduit must be the same. We can add here also conduit. Conduit, if you put them in a conduit, and you cannot parallel this than 1 aught, A, W, G, or more. When you parallel, you cannot parallel mat less than 1 aught. Can I get you guys to look at these and understand them? When you parallel conductors, the insulation is the same, the size is the same, the length has to be the same. size, material, copper, all the coppers together, terminate in the same manner, conduit must be the same, and not less than 1 aught. That's your rules for parallel conductors. If you don't do this, Adam, if you put one conductor in a metallic conduit, you will do induced heat. You will conductor will induce eddy current. You will basically create an induction heater. If you take one phase A and put it in an EMT conduit, steel EMT conduit, and put 100 amps into it, and you go touch the conduit, it will be hot. You're creating an induction heat. To avoid creating an induction heat, you know what the smarter than Chad would do? They'll put phase A, phase B, and phase C, and a neutral. So that will be phase A, phase B, phase C, and neutral all together. What this will do, guys, the magnetic field of all these three conductors and neutral, they cancel each other. Who cares? You shall not get the induction heat. No induction heat. Remember that. Always all the phases of the same circuit, put them in the same conduit. Now what happens if it's PVC? No induction heat. So this is in ferrous materials, basically. If it's an aluminum too, it doesn't work. Aluminum conductor. Only steel conductor. You want to avoid that one in steel conductor. So a lot of people, guys, group them together in one. Here's what we're talking about, guys. Look at this conduit. You have phase A, phase B, phase C coming in every conduit. Phase A, phase B, phase C, and here, and here, and here. And then they split to the phases. That's how you parallel conductors. Same material, everything is the same. Okay, so we know how to parallel conductors. Before they commission the building, Derek, and before we energize a 4,000 amp switch here, do you think they just go say, yeah, now we install them, they'll go flip the switch? Seriously? And blow up half of the building? The smarter than Chad, they do, guys, commissioning on these bigger buildings in an industrial project. The part of these commissioning is they measure the insulation. What if we send an apprentice like my friend Adam there, and while he's pulling the conductors, a hole went right through the conductors, and he got scared. He didn't tell his boss, and he just put it in the conduit and move on, right? And you go energize, you have a ground fault. You will burn part of the feeder. Bad day. So in order to make sure that the electrician guys did not do any mistakes, they did not terminate or they terminated wrong, they do an insulation test. They test the insulation. Very, very important. The way they do it, the mega ohm meter, they have a machine, and they pump DC voltage. Literally, they put DC voltage in the wire. They disconnect the load, they put DC, so they take phase A, phase B, and put a DC wire between them, and it will give you how good the insulation. Did Adam screw up the insulation while pulling the conductor or not? If it's, and they test A to A to B, B to C, all the conductors with the ground, test them one at a time to indicate that the insulation is good. They do them also with the ground. You don't have a ground fault, so you take every phase to the conduit or at the end to the ground and they test it. Each conductor should be tested with the other conductor as well as with the ground and the conduit. So phase A with phase B and C, and phase A with the ground conductor, the wire, and phase A also with the neutral, and phase A also with the conduit. And then you go to B and you're going to go to C. Make sure they're not you're not shorted. Here's how they do them. They crank most of them are batteries, guys, and they sink a DC voltage right through them, and that DC voltage goes in, the current comes back, measure the resistance. The resistance between these two wires at the end, they are open, guys, they're not connected. So what do you expect the resistance between the two wires when it's open? Very high, huge, in mega ohm. If it's not in mega ohm, then if they short right here in the middle of the conduit, they're shorted, then this will show a very small resistance that will indicate this Adam or Derek, when he is pulling him, screwed him up. So go pull this feeder and check it. Very clear. You're talking, guys, about hundreds and hundreds of runs of cables. Do you think we're going to trust an apprentice pulling these and not making a mistake and go energizing it? So they do tests before they energize. Every phase. Look at that. They go every phase with every other phase, then phase with the conduit. Can you just see that? Now here's my conductor here. Should this conductor be tied to the conduit? It shouldn't. If it's tied to the conduit, this should show a very low value. That's ground fault. They will tell you, oh, phase A has a ground fault on it. Go pull conductor A and you look, oh, the insulation again was damaged. Somebody cut through the insulation before you energize it. What if you don't do this, guys? What happens if you don't do this? You're just going to have a short ground fault or a short circuit. Okay, so that's the testing. The last thing, guys, is the American wire gauge. How did they come up with the American wire gauge? In most of the world, they use squared millimeters to gauge the wires. We use American wire gauge for the solid wires and also for the stranded. The gauge coming from, important for determining, the gauge will determine the current ability, the current capability or ability or ampacity of the conductor. And the way they come up with the gauge, 14 gauge, always bothered me, Derek, 14 and 12 gauge. What they do, they determine the number of, they have draws, they draw a wire necessary to produce the diameter of the wire. So they keep putting these through dies. Look at this. They bring a wire here, and they put the wire right through these dies, and they keep making it smaller and smaller and smaller. And at the end here, oops, we are gauge 14. Right? Depending upon how many dies they put them through and draw that wire through these dies, it will determine is it gauge 14, 12, 18, or 500 kcm. Can I get you guys to understand that's how they come up with the gauge wire, the American gauge wire, coming from the old days of the steel. It has been there for almost 100 years, guys, that method. Okay, this is the rule. These were, they determine what size conductor, guys. Here, you put your conductor right in here. If it fits here, this will determine what gauge wire and what's the diameter of this conductor is. Here's how it looks like, Adam. So if you have number 14 wire, if you put number 14 wire right in here, and it fits, this conductor is number 14. We don't use 15 and 12 and 16. We use certain, that's how they determine it. FYI, not a big deal. Not the whole. They put them, and in the other side, if you put it here, this will give you the diameter. Is that what the gauge listed? in inch, in the wire in thousands of inches. So that will give you the diameter. The diameter in thousands. So this is 0.064 thousandths of an inch. The diameter of this conductor. Anyway, that's will get you the AWG. The slot. When you put your wire, can you guys see? It's not. You don't put the wire here. You put it right here. That's what determines the gauge of the wire, not the hole. So there's a hole like this. You don't put the wire here. You put the wire right here. That's what determines the wire for number 14. Not here. Here. Not here. I used to think it's they put it in that little hole if it fits. Okay. So that's basically, guys, the ampacity. I hope before you graduate from Dunwoody, you know, guys, how to use 310.15b16, all the derating tables and what's not. I know if you guys read the chapter, there are calculation about ampacities and also calculation about voltage drop. Tomorrow, I will go over these calculation. Let me see if we have a couple of graphics that we did not go over. I thought we did over most of them. Okay, the K factor, the K that they use, guys, and look at this one. For aluminum is typically 17, or sometimes it's seen as 21. And for, where's my copper? My copper is 10.4. And with a temperature coefficient, then if the temperature changes, these values, guys, change. We'll talk about this tomorrow. These are the K factor that they use for voltage drop. We'll talk, but these are tables. Give you the iron if you're using iron. Look at the, if you look at the resistance you're using iron compared to the copper and aluminum. How about mercury? My God, how are you going to pull the wire through mercury? So you can see it almost the copper. Gold is good, but who wants to put, do you want to really put gold wires? You expect them to stay there? We barely can keep the copper sometimes in the conduits, let alone gold. Okay, the second table that you guys will be using tomorrow with your friend Chad is table 8. For table 8, Adam, when we do the calculation, I'm going to emphasize, and you guys have seen this table before, I'm going to emphasize one little thing, guys, for voltage drop. Look at this. Let's just say number 14. Here's number 14. I have stranded 7. From here, my friends, you can go to uncoated copper, and you come over here, ohm per kilometer, ohm per kilofoot. That's what you're going to default to all the way up to here. So this is the resistance of number 14 conductor, the R. So when you do the calculation tomorrow with your friend Chad, you're going to find a formula that says voltage drop equal to rel, R-I-L over 1,000. So when I butch this formula, guys, and I say find R for number 14, here's R for number 14.
So Derek, if the conductor was solid, can you guys see the solid conductor number 14 here? It goes with the upper number. Can you guys see the difference between solid and stranded? So you grab these and you put them in this formula, you got your voltage drop. This is what we're going to be doing calculation-wise tomorrow. This is similar to voltage drop equal to KIL over CM. Either you use this formula, Adam, or this formula. Any one of them will get you the voltage drop. If you're using the lower formula, the KCM for number 14 is right here. Can you guys see? This is what will give you the KCM for number 14. This is also very, very important area, circular melt area. So you're going to see Chad talking about these when we do the calculation. So we talked about number 8. Is it number 8? We have number 8, property of conductors. All right, so we talked about the ambient temperature correction, bundling. We talked about all these, insulations. Okay, that's all what I have. I think we're good. Any comments, guys? Any questions? I know I spent some time on that. I really hope that this chapter, you guys will go over it with the calculation that we're going to do tomorrow. What I'm hoping is, hopefully, it will be the last time you're going to see Chad talking about sizing. Any comments, guys? Any questions about the ampacity and using them? Third time touching that concept, guys, with a couple of examples tomorrow. Hopefully, stick. After that, you're on your own. Derek, Adam, Matt, cool? All right, the rest of the day, we're going to spend it, guys, developing the riser like we did yesterday. You're going to finish your risers and the low voltage. I want to say a few things about low voltage today or tomorrow morning. If you anybody started low voltage, do you guys start low voltage? Okay, well, not we focus. Then let me do that one tomorrow morning. If you want to start, you go copy it and start modifying what you have. When they say modify, adding the number of smoke detectors and the number of contacts on the same zones. I just want to change a few zones a little bit, add more zones. That's all. So, but I'm hopefully you guys can finish the power at least today. Cool? So now you start working on your project. You were stealing working on your project, guys, if you do it before 9:30. Cool? All right. Thank you.